Hello again, problem solvers. We're in lesson 18, counting. So we're going to do combinations and permutations and different ways to count things with factorials, the Mississippi problem, and all those things. So I'm hoping you've got the ice sheet in front of you and you've already watched the PowerPoint. And I'm just going to talk through the problems here. So first one has a bunch of different variations for 8 boys and 9 girls to sit in a row of 17 seats. And the first says how many different arrangements are there? Well, if they're just sitting and you don't care who sits by who, there's 17 options for the first spot, and then 16, and then 15, because the 17 things are on a row, and order matters, so that's just 17 factorial. Another way to think about it for permutations is that 17 permutes 17. Now, the next way says how many different seating arrangements if all the boys sit next to each other and all the girls sit next to each other? Well, you either have to pick boys or girls to start, but let's say you do boys first, then the boys sit in a row, and then the girls sit in a row. I'm getting bored of writing this, but I'll finish it out. So that's 8 factorial times 9 factorial. But you could switch them, right? So I could put 9 first and 8 first, so there's double. I basically have to add this. This is a disjoint situation from adding and then doing 9 down to 1 and then 8 down to 1. So you can think about doubling, or you can think about this plus that, and it's 2 times as many because it's the same thing twice. All right, the third scenario is you want boys and girls that are sitting by people of the same gender. So this is similar to before, but you have to do there's 17 seats. You have to start with the girls, so that the first and last seat is a girl. So you have 9 options then for a girl, then you have 8 options for a boy, then you have 8 options for a girl, and you have 7 options for a boy, and I can keep writing this out. But you're going to see 9 factorial there, and you're going to see 8 factorial here, and I encourage you to write that out if you don't see it right away. So then the last one is you're going to end on a girl. You're going to have 1 option. So this is going to be 9 factorial times 8 factorial for this case. All right, so that's question 1. Next one says, between 1 and 1 million inclusive, which are more numerous? Integers whose base 10 representation, so the normal way you write an integer, contains a 1, or those that do not. How many of each type are there? Okay, so if you think about, you have 6 spaces, so forget about a million for a minute, but in general you have 6 digits. And how many ways can you fill? I'm not going to put, if I decide to not use ones, how many ways can I fill these spots? And think of like 2 as 0, 0, 0, 0, 0, 2, like that, right? So I have 0 through 9, but not 1. So I have 9 options for each of these if I'm trying to not put a 1. So that'd be 9 to the 6th. However, 0, 0, 0, this one I really shouldn't count because that's 1. It's 1 to a million inclusive, so take that 1 number away. Okay, so this is, notice it's much easier to count the numbers without a 1 because I don't know where the 1 should be. But if I know none of them have a 1, this is easy. So thinking about the complement, the other thing, is a very important trick for counting. It's much easier to count the ones that don't have a 1. Okay, this number is 531,440. And so I need a number that adds to the million. This is without 1s. The ones with 1s are 468,560, right? Okay. And up here I didn't count 1 million, but we knew 1 million was what the other case, right? It has 1 in it. And so these are the numbers with 1s in their representations. That one's a little strange, and an important concept about thinking about the complement, the other stuff. And so chew on that one for a while. And feel free to ask me if you have questions. All right, the next one, number 3, I want to have a circle, and I have endpoints chosen on a circle. So here's a circle. All segments are drawn between all pairs of points. No 3 segments intersect at the same point. Okay, so if I have this, so if I do that, and I do that, and I do that, and I do this, and I do this. So I want no 3 segments intersect at the same point. So I don't want to go through this point again. So if I do this, of course I'm terrible at drawing, that's okay. But I need to make sure, as these points grow, I need to make sure I never go through these points again, that I never have 3 points connected. Okay, if that's true, how many points do these segments intersect in the interior of the circle? Okay, so if you look at the way I just drew it, so actually let's go back up a step. So when I had 4 points, I get one and only one pair of segments that intersect and have the given 4 points as endpoints. That's this, right? When you look at this thing, look at this little sub box. I get that thing, and then take these 4, and I get this thing. And each of these little guys corresponds to a group of 4. Pick 4 at a time, and then you create this shape, and you get that intersection. So this seems kind of so easy, it's hard, but you take the number of points, choose 4. Order doesn't matter, but if you choose 4 vertices, you make 1 point of intersection. And notice when I have 5 of these, 5 choose 4 is 5. There's only one way to do that, or 5 ways to do that, excuse me. You basically choosing which one to leave out, right? And you get 5 here. Let's just check it one more time. If I do 6, so 6 choose 4 would be 6 factorial over 4 factorial, 2 factorial. So that would be 6 times 5 is 30, divided by 2, you should get 15. This is going to be tough. Let me try to draw this well. You guys know I can't draw. Hopefully these don't intersect. They're common spots. Just barely not. I will probably forget some spots, but that's okay. I'm going to go straight across. This needs to go straight across. So each of these should have 5 things coming off of it, right? 1, 2, 3, 4. So this guy, I forgot 1. And this guy I also forgot to go down there. There's technically 2 down here. I just can't draw very well. Okay, so let's see how many I got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are real hard to see down here, but that one goes across all 3 of those, so 13, 14, 15. I just drew those terribly down there, but looks reasonable to me. Even when you think you got the pattern, it's worth checking. Of course, you have to do 7, but this is getting really old, right? So you could just do a bunch of these and try to find the pattern for the number, but you kind of have to use this interpretation, otherwise it's going to take you a very long time to see the pattern. Alright, so let's go ahead and go to number 4. So it says each side of a square is subdivided into 101 segments. So I'm not going to draw that out. I'm not going to waste your time with that. But here's a bunch. There's 101 segments. And so it says find the number of triangles that are the vertices of these 400 points of subdivision. First, I want to back up a step and do something smaller and explain why there's 400 points of subdivision. So if you think about, let's say we did 2 segments. So you split your guy up like this. You would need 3 points, but you're going to reuse these points. So if you did this for a square, this is what they're talking about. There's only 8 points total, so 8 points. So there's 400. There's 4 times this, right? And if you did this for 3 segments each, let's take a look at this guy here. You would have 1, 2, 3. Okay, so you'd have 16 points of subdivision. 1, 2, 3, 4, 5, 6, 7. So you have 16 points, and now what do you do? But the thing about the phrasing is that they say of subdivision. The corners are not subdivision points. So here, when you do 101 segments, you have 404 points, but don't use the corners. So when you go way down here, those are not points of subdivision, those are just the corners. So you have, when you have the rest, you have 400 points of subdivision. Okay, so I just wanted to explain where that number comes from, make sure we have the problem set up. And now let me make a new square here. So here's some points. Pretend there's 101 of these. Or 400, I guess. 404 altogether. Blah, blah. Okay, so I want to know how many triangles have their vertices at the points of subdivision. Okay, well, first off, there's two types. You could do something like this, where every vertex is on a different side of the square. Or you could do something like this, where two are on the same side. So we want to count these separate. So if you do these, if you take this one, where you have, out of the 4 sides, you're going to pick 3. So that's 4, choose 3, which is 4. You can also just think of, choose one of the sides to leave out, right? So choose 3 sides to use. And then for each side, choose one of the 100 points of subdivision. So that's 100 times 100 times 100. So that's the first kind. Now the separate kind, this is a separate thing in disjoint case. We're going to add what to do in the situation, in the second situation. Okay, so you need to choose a side, and there's 4 ways of doing that. So this is side 1. And then make that the side that has the 2 on it, right? It's like 2 points on that side. And that's 100, choose 2. Order doesn't matter, I don't care which one's which, right? I'm just going to connect them. Then you need to pick a different side. There's 3 ways to do that because you already used one side. Order matters here. And then select one of the points on that side. Well, you've got 100 options there. That crazy number, after you do all that stuff, is 9,940,000, almost 10 million. This is a pretty crazy combinatorics problem. You also have to kind of see the geometry, but there's important concepts for combinatorics here. Picking a side, picking another side. When they're different, you kind of do things in order. When they're disjoint cases, you add them. A lot of important concepts in this problem. All right, so that's the end of the ice sheet for counting.